All right, so when we're talking about chemical bonding and really chemistry in general, it's the electrons that do everything. When we change one compound to another compound by using chemistry, all we're doing is moving around the electrons. The atoms themselves, the nuclei, generally don't change. So if you have aluminum in the beginning, you have aluminum in the end. The thing that's changed is its electronic structure. And if we think about which electrons are doing the work, remember that we said that the core electrons are tightly held, and they're actually too tightly held to really do anything, right? So they just kind of sit there and don't really participate in chemical bonding. So we really only care about valence electrons. So let's take a look at our periodic table. Copy that down. Yes, it did. And we're going to draw what are known as Lewis symbols. So a Lewis symbol describes how many valence electrons our element has. So every dot that we're going to draw around our Lewis symbol is one valence electron. So for example, if we think about lithium, lithium is in this first row. It only has one valence electron, so it only gets one little dot around it. Right, next column over, beryllium has 2 electrons, so we draw 2 dots. Note that we don't pair them up, we put one on either side. It doesn't necessarily have to be left and right. It could be top, bottom, top, right, whatever, but don't pair them up. After that, we have our third column with 3 electrons, boron. After that, we have our fourth column with 4 electrons, right? Carbon, silicon, that kind of stuff. After that, we have nitrogen. Note that we only have 4 sides here, so at this point, we start pairing them up. Oxygen has 6. Right, our halogens, for example, fluorine, have 7. Again, it doesn't matter where you put that lone dot. And then finally, our noble gases have 8. And remember that we said that our noble gases are particularly stable because they have a filled valence shell. And this is most often called an octet. Octet for 8 because there's 8 valence electrons. But it's not that they necessarily want 8 valence electrons, it's that they want a filled outer shell, right? So elements, want this, right? They want that filled valence shell. This is what's known as the Octet Rule. I'm going to put rule in these kind of air quotes because really it's more of a guideline, right? We call it a rule, but we're going to break this rule all the time. For example, hydrogen and helium, neither one of them want an octet. Neither wants 8 valence electrons. If we think about how many valence electrons it wants, hydrogen and helium both only have the 1s orbital. And so it has a filled valence shell when it just has 2 electrons. And same thing for like lithium, right? Lithium wants to become lithium plus. If you think about it, then it only has 2 valence electrons. So it's not really, the octet rule is what we learn, but it's not necessarily the octet rule. It's, again, just a filled valence shell. All right, so let's take a look at ionic bonding. So remember, in ionic bonding, we have metals and nonmetals. And remember that metals, they want to give up an electron, or at least it's easy to remove an electron. Whereas a non-metal, they don't want to give up their electrons. And in actuality, they actually want more electrons, right? Think about our non-metals. They generally have a negative charge to get that filled octet. And so if you have something that doesn't really want electrons and one thing really does want electrons, well, what's going to happen is we're going to transfer some electrons, right? If the metal gives up some of its electrons to the non-metal, then both of them can have that filled valence shell. So for example, if we have potassium with its 1 valence electron and chlorine with its 7 valence electrons, if this potassium were to simply give up its electrons to chlorine, both of them would be really happy because both of them have a filled valence shell. And so then what we end up is a positive chlorine or positive potassium, and then a chlorine that has an octet. and of course a -1 charge. This is what's known as a Lewis diagram, and we're showing the electrons. The chemical formula would simply be KCl, right? We've got 1 chlorine or 1 potassium for every 1 chlorine. And both of these have a filled valence shell, right? That's very easy to see with the chlorine because it's got 8 electrons around it. But if you think about this potassium, it too has a filled valence shell. So the electron configuration for potassium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. And then when it becomes an ion, it gives up that electron. We get rid of that 4s electron, and boom, right here, we've got a filled valence shell. Right, in this case, an octet. All right, let's take a look at some more examples. So what if we had a sodium and then an oxygen, right? So sodium has 1 extra electron that it kind of wants to get rid of, while oxygen is 2 electrons short. And so what's going to happen is we're going to need more sodiums to fill up that valence shell of oxygen. We're going to need 2 sodiums, right? So we're going to draw another sodium here. So we're going to have 2 sodiums. They're each going to give up their 1 electron to oxygen, and it'll become then 2 Na pluses, and then 1 oxygen with its filled valence shell. So if we think about the chemical formula there, it would be Na2O, right? And so these ionic compounds will always have ratios so that we have a net neutral charge and everything gets its preferred charge. Let's take another look at an example. We have aluminum with its 3 electrons. We have oxygen with its 6 valence electrons, right? So aluminum has 3 extra, while oxygen is 2 short. So how do we know which ratios they're going to mix into? It's very easy to kind of do. What you do is you take the number of extra electrons that you have, and you're going to have that many of the opposite element. So aluminum has 3 electrons. That means that we're going to have 3 oxygens, and then vice versa. Oxygen is 2 electrons short. That means that we're going to have 2 aluminums. So we're going to have 2 Al3 pluses, and then 3 oxygens, which are 2 minus. And then if you add up all those charges, you get to net neutral. And so the formula here for aluminum oxide is Al2O3, right? Each aluminum is +3, each oxygen is -2. If you sum those charges, they get to 0. So you can do this little quick trick just to figure out the chemical formula for any ionic compound. The only thing that you have to be careful of is you always reduce the formula to the lowest numbers possible. So what do I mean by that? So if you try this trick on calcium and oxygen, right? Calcium has 2 extra, oxygen is 2 short. So you might think that the formula is Ca2O2, but that's not the correct formula. Note that both of these numbers are 2. We can reduce this formula. We can divide both of them by themselves by 2, and it can just become CaO. So that's the real formula for calcium oxide. So that's just the little caveat to using this trick to figure out the formula. You'll also often hear ionic compounds called salts, right? So if you say this is a salt, this, what you're talking about is just an ionic compound. In regular kind of, just common day talk, right, we mostly refer to salt as sodium chloride. That's what table salt is. But any ionic compound is indeed a salt.